There's a persistent idea in modern education that teaching robotics requires serious capital. The assumption is that to bring technology into the classroom, schools have to purchase expensive, proprietary kits, locked inside closed ecosystems. The result is that underfunded regional schools, like those in cities like Arequipa, look at those price tags and back away. They abandon the idea of teaching 21st century skills entirely because they feel priced out of the market. But that financial barrier is an illusion. It is a narrative maintained by commercial entities, relying on high-margin hardware to keep schools buying their specific, branded parts year after year. A school's budget does not dictate its capacity for technological innovation. We have to separate the practice of engineering from the business of selling educational toys. When we let the price of a branded kit stop a robotics program before it starts, the true cost is the lost intellectual potential of students who are denied the chance to practice logic-based problem-solving. There is an alternative approach that bypasses this expensive model entirely. It is rooted in the maker education movement, a grassroots philosophy that prioritizes resourcefulness over prepackaged solutions. In a classroom, this looks like adopting open-source hardware. Instead of buying closed kits, students get unrestricted access to raw electronic components, items like individual motors, various environmental sensors, and bright LED lights, costing a tiny fraction of proprietary setups. At the center of this democratic shift in engineering is a small, inexpensive piece of hardware known as a microcontroller. Think of it as a blank digital brain, waiting to be given instructions. Building circuits from the ground up forces a shift in perspective, where the internal logic of a machine becomes as accessible as its outward function. This is the Arduino Uno, a low-cost digital brain for educational robotics. Look at the black headers along the edges. These digital and analog pins act as its sensory nervous system, receiving data and sending commands to motors or lights. Because the software is open source, students can program this brain freely. Beginners start by dragging and dropping visual blocks of code, while advanced students write text-based instructions in C++. That programming directly translates to visible action. A student writes a sequence and uploads it, and a physical circuit of glowing LEDs or spinning motors comes to life right in front of them. This requires zero specialized tools. Instead of using a hot soldering iron, an obvious safety risk, students plug wires directly into a plastic breadboard to connect components safely and temporarily. By connecting wires to those input and output pins, students are learning the foundational vocabulary used in all modern industrial automation. Compare the rigid cost of proprietary kits against a modular Arduino ecosystem. A commercial kit costs over 350 sols per student. With Arduino, students recycle the mainboard each year. Schools only add a tiny cost for new sensors, drastically driving down long-term expenses. In practice, this means the exact same microcontroller used to build a battling sumo robot in year 1 can be unplugged, reprogrammed, and wired up to monitor environmental temperatures in year 2. For schools operating with absolutely zero initial hardware budget, they can turn to Tinkercad. It is a completely free digital simulation platform where students build and program these exact circuits virtually before ever touching a physical wire. This modular approach drastically lowers the entry cost for any institution, ensuring a lack of luxury funding no longer excludes students from crucial technological literacy. Ultimately, the functional robot sitting on the desk is only a byproduct. The real value lies in the rigorous cognitive process required to get it working in the first place. When a circuit fails to light up or a motor spins backward, students are forced to stop and troubleshoot. They trace their wires, debate solutions with their peers, and develop a genuine resilience to failure. Writing logical, step-by-step instructions for a machine directly strengthens their mathematical reasoning. They learn to break a massive problem down into small, executable commands. Robotics takes the abstract concepts of math and science and pulls them off the whiteboard. It turns passive learning into an active, physical challenge that delivers immediate, tangible feedback. The traditional roadblocks to STEM education, high costs and intimidating complexity, have been dismantled by open-source hardware. Educators who start with these modular tools can build technical proficiency in tandem with their classes, using open-source guides to bridge the gap between initial curiosity and project execution. When hardware is no longer a cost-prohibitive mystery, students can focus entirely on the complexity of the problems they want to solve, from smart agriculture to advanced medical prototypes. It is time to step away from closed ecosystems, embrace open-source hardware, bring these practical tools into your classroom, and start building the future.